Hey everyone, welcome back to The Explainer. Today, we are diving right into Chapter 10, vibrantly titled Elephants, Tigers, and Leopards. And honestly, I'm super excited to guide you through this one, because it takes a really playful, almost unexpected path to foundational math. We aren't just staring at dry numbers on a page today, no way. We're going to play games, uncover some pretty magical number patterns, and literally trek into the wild to solve massive, real-world problems. Let's get into it. Okay, let's dive into this outline and map out our journey. We've got 4 main stops today. First, playing the NIM game. Second, discovering addition chart patterns. Third, reverse and add number tricks. And finally, wildlife word problems.
Starting off with Section 1, playing the NIM game, the interactive hook.
So instead of kicking things off with an intimidating wall of equations, which, let's be real, nobody wants, this chapter hooks learners right away with a strategic 2-player game. Look at the energy here with these students actively engaged with a NIM game on a chalkboard. It brilliantly brings math directly into a social, competitive space. It totally lowers the barrier to entry, right? Because they're calculating, they're strategizing, and they're actually having a blast all at the same time. All right, so how exactly does this game work? It's delightfully simple, but actually really strategic. Here's the deal. Player 1 starts by choosing either the number 1 or 2. Then, player 2 gets to choose either 1 or 2, and they add it to player 1's number. You just keep alternating turns, always adding just a 1 or a 2 to that running total. The ultimate goal? The first person to reach exactly 10 wins the whole shebang. Sounds super easy, right? But it actually forces you to constantly look ahead and kind of predict your opponent's moves. But let's go a step beyond just playing it. Imagine you're in the middle of a game right now. Can you guarantee a win if the other player has just reached a total of 6 and it's your turn? What if they reached 7 or 8? Take a second and actually mentally play along with me. If they're at 7 and you add 2 to make it 9, well, they'll just add 1 and win, right? But what if you add 1 or 2 to force them into a corner? This simple little addition game is actually an incredible exercise in working backwards from a target number. Moving right along to Section 2, discovering addition chart patterns, finding the hidden rules. So transitioning from the competitive edition of the NIM game, we uncover the magic hidden inside structured number grids using this fantastic visual tool called the window frame. Imagine placing a small, square frame over a giant table of numbers. Instead of getting completely overwhelmed by looking at the whole chart at once, you're guided to isolate just specific little sections. You explore the rows, the columns, and the diagonals just inside that tiny window. It is a brilliant technique for really focused analysis. Now, what's really interesting about this grid is how the intersections of the rows and columns create these totally predictable outcomes. For instance, the intersection of row 2 and column 3 gives us 5. But look closer. Check out the diagonals. You can literally see the numbers repeating themselves diagonally, like 2, 2, 2, or 3, 3, 3, flowing right from the bottom left to the top right. It's like the structure itself is secretly teaching you the rules of addition. And this grid opens up some really cool pattern-finding missions. For example, try to observe the cells where the number 9 appears, like how many times does it show up? Or try to find rows or columns that contain only even numbers or only odd numbers, and then figure out why that happens. You can even sum up the numbers in the diagonals of those window frames. Emphasizing these specific observations is absolutely crucial. It builds real analytical skills, shifting away from just boring rote memorization to genuine mathematical discovery. Next up is Section 3, reverse and add number tricks. The magic of reversing. Okay, let's take that abstract pattern recognition we just talked about and turn it into something that feels almost like a magic trick. Pick any 2-digit number. Let's use 27. Take that original number on the left and simply reverse its digits. That gives us 72 on the right side. Now, right now, in your head, add those two numbers together, 27 plus 72. The result is 99. I mean, it's such a surprisingly neat and patterned result. Try repeating this with a bunch of different 2-digit numbers. When you add a number to its reverse, you start seeing these repeating digits over and over, these beautiful multiples of 11. It's a really simple trick for sure, but it perfectly reveals the underlying elegance of our base 10 number system. And this trick naturally opens the door to some great follow-up challenges. For instance, list all the numbers which, when added to their reverse, give a sum of exactly 55. Or, hey, what about 88? Can we even get a 3-digit sum? And if we can, what's the smallest 3-digit sum we could possibly achieve?
Posing these kinds of questions expands a simple party trick into much broader algebraic and critical thinking. And that brings us to our final stop, Section 4, Wildlife Word Problems, Real-World Applications. Now this is the climax, where all these foundational number skills we've been building get applied to large, real-world data sets. We are no longer looking at abstract grids on a page. No, we're looking at majestic elephants, tigers, and leopards out in the wild. This re-anchors the abstract math back to a thematic, visual world, giving the numbers physical meaning, which is just so vital for keeping things engaging and memorable. Take this specific real-world problem, for example. We're told that Assam has 5,719 elephants. We are also told that Assam has 3,965 times more elephants than Meghalaya. The challenge here: calculate exactly how many elephants are in Meghalaya. We are dealing with full-on 4-digit subtraction now. That is a massive step up from our little game of NIM. So the crucial point is this regrouping rule right here. Regroup 1h equals 10t, and 1,000 equals 10h. What this really means is that to subtract these large numbers, you have to understand that 100 can be regrouped into 10 tens, and 1,000 can be regrouped into 10 hundreds. This is literally the secret tool needed to unlock complex 4-digit subtraction. It's not just mindlessly crossing out numbers on a page. It's about physically trading values. And by applying those new math tools and carefully taking away 3,965 from 5,719 using that regrouping method, boom, we arrive at our final answer. There are exactly 1,754 elephants in Meghalaya. I have to say, it is incredibly satisfying to take a massive, intimidating block of real-world text and distill it all down to a single, precise, calculated truth. So, what does this all mean? Well, I want to leave you with one final, kind of provocative thought from the source material. Can you solve these massive problems by noticing the ways numbers increase and decrease without even using the standard algorithm? It's a really fascinating challenge. It asks you to look beyond the rigid, step-by-step formulas we're so used to, and instead see the deeper, flexible, and playful mathematical connections we've been uncovering today. Think about that the next time you're faced with a tough math problem. Thanks for joining me on this explainer, and keep exploring those patterns.